Hi everybody. Thanks, Jakob, for the introduction. I'm Henning. I'm one of the co-founders, and I would like to talk with you about how we can test microservice architectures, and I'd also be very interested in discussions and feedback from you. So this can very well be an interactive discussion. So we have some room for discussions planned at the end. So please don't hesitate to jump in and share your opinions and share your experiences. So let's get started. So I assume everybody can see the slides. Why microservices? There's basically, the biggest need for microservices is really an organizational issue more than a technical need. So there's rarely a technical need to split stuff up, except for if you grow too big and you have too much scope for one team to handle, so that you need 2 teams, and then you need 3 teams, and then you have 10 teams, and all these teams need to be managed. And all these teams need to contribute features in their own pace, and you want to empower the teams in a way that each team can fully own the delivery process, ideally. And so there's the question of how big should a team be? That's been answered by Jeff Bezos in a way that if you can not feed a team with 2 pizzas, then it's too big. So at least at Amazon and also at lots of other companies that adopt that kind of mindset, teams are very small. They're like 5, 6 people that own a couple of microservices, at least one, and they contribute to that microservice, and that microservice or those microservices then contribute functionality in a microservice architecture. So basically having lots of microservices is just a function of a good way of scaling up your team. And then you have basically Conway's law that states that every architecture is then is reflected, or technical architecture is reflected in the organizational architecture and vice versa. So looking at the microservices then gives you an idea of figuring out how teams collaborate and create value. So that sounds great, and there are tools to then dig into how microservices interact with each other. But the difficulty arises from the added complexity of microservices. So instead of having just one monolith and one function call, and those are the entry points and those are the exit points, and we know how to somewhat test the monolith, so which is the kind of opposite paradigm of we have one big application. You have more things that can go wrong. And especially can go wrong in a security issue where you have microservices depending on having inputs formatted in a special way. So basically, one microservices relies on the information being checked, or some kind of security sensitive information being checked by a preceding microservice. But since you can just plug and play them together, there's no reason why this microservice shouldn't be exposed to the world directly, or this some filtering, some validation changes in one microservice that has effects on what some other microservice is doing. And especially if you have these highly decoupled, empowered teams that have full ownership over their microservice, and they test their services, and then there's kind of some integration and some smoke test that tests for functionality before deployment, which is how you usually set it up. Then it's really hard to security assess this interacting web of services. Testing for security is always hard, but it's especially hard when you tackle microservices, just because the interactions and the interdependencies are much unclearer and less known than you have it in a monolith setting where you can look more easily into core stacks and stuff like that. So how then do microservices get tested? Well, there is there's the usual toolbox. For each service, you can have unit tests. So you should have unit tests, which tests this service in isolation and more or less mocks away the other services. So there, it's nice for functionality and for driving out features using test-driven development. You can iterate quickly. You can be sure that you landed on a good solution for your problem. But basically, your assumptions or your team's assumptions about what the other teams and the other services are doing and how they are behaving and what kind of data they are sending to you is encoded in how you mock these other services. So in reality, this assumption might change. And if the mocks don't change, you have this mismatch of behavior during unit test runs versus behavior in the real world. And this is where bugs work, and especially this is where security issues work, because the problem with security vulnerabilities in particular is that they break the assumptions that the programmer had in a dramatic way. So when you look at popular vulnerabilities that made the press, it's hard to say popular because they cause lots of pain, right? When you look at very well-known security bugs, like for example, Heartbleed, that was a misconception in the OpenSSL code about what kind of trust to put into the response length field for this heartbeat message. So heartbeat that caused then the heartbeat bug. So in this tells you, and there are stories like that all over computer science history, so to say, but basically misconceptions about the kind of data that you receive causes bugs and causes security issues. So unit tests are obviously not the right choice for testing for security. Then you have API tests, or you have Wrestler, which is testing individual services at the API level. You can do code reviews. You should do code reviews, especially for security critical infrastructure. And then you have things like Burpsuit that are black box testing APIs. You can tell it one endpoint, and these tools will then generate random input against this one API and see whether or not the service crashes. And the same is true also for OWASP-ZAP, which is another black box scanner. And so you can get some amount of testing through unit tests, integration tests, system tests, and black box fuzzing. But the new kid on the block, so to say, in terms of security testing, is fuzzing or fuzz testing, because that actually turns this one-directional arrow of I give the service input, and then I have no idea what the service is doing, into a two-way road where the service can then, or the function under test, system under test, can tell the fuzzer, this is what I did with the input, and therefore the driver that generates the input can generate much more input and direct the inputs into many different paths. So instead of just 60% code coverage, you get 90% code coverage. So let me show you how that works, starting from the basics. So the idea is that the fuzzer sends inputs to a program under test and watches its behavior. So those are the two components that you always need for fuzzing. For sending the input, you need something that generates new inputs from existing inputs. So I'll explain a little bit what genetic algorithms mean by have to do here. But it basically looks for structures, looks for inputs in the software under test, and the behavior watching aspect is basically the feedback. So it watches for crashes, for memory safety violations, and custom bug detectors. So those are the sanitizers, basically. Is something bad happening in the program? And most importantly, it also gives coverage feedback back to the fuzzer. And this coverage feedback is actually what drives the genetic algorithms, because in genetics or in like Darwin discovered, you have a fitness function. So you know how good is some input based on how much coverage does it generate. So how deep does this input get into the execution of the program? Like how many lines of code does it execute? How many statements does it execute? And then the genetic algorithm looks at a generation of inputs and selects those inputs for the next generation that have the highest fitness functions, and the rest are then discarded. And by this simple algorithm, the fuzzer can generate more and more complex input that more and more resembles the domain of the program. So how does it look like for an image parser? So assume we have a function that, or if you want, a microservice that parses images and does something with them, like returns the metadata to the caller or resizes them. And for some reason, it needs to read the image data. So how the fuzzer tests this kind of functionality is by giving it random input at first, so 0, which returns in a broken image. But because it not only bombards the program with random input, but also generates better inputs from the coverage information, it quickly learns that the input always needs to start with some magic bytes, which may make up the image format. So then, after a few generations of inputs, it generates a green image, or a blue one, or a red one. And time by time, it generates input after input after input, mutates the inputs based on the information that the program gave it, and then from nothing generates like a stream of images that you have as test data. So in a sense, this coverage-based feedback gives you a automated test case generator for your problem domain, whatever that may be, and an in-process error detection. So fuzzing was first very, very popular for memory unsafe languages because they have many footguns in C and C++ regarding memory safety. And it was widely assumed that, okay, this is where it ends, right? This is what it's good for. Until Code Intelligence published Jazza, so it's an open source project which brings the fuzzing technology to the JVM, and the JVM, of course, being memory safe VM, and especially hosts memory safe languages like Java, Kotlin, Clojure, or Scala. We found, or in the Google OSS Fuzz project, we found lots and lots of bugs with Java. And those are, of course, not memory bugs, but parsing bugs, out of memory issues, so where you have memory leaks, or issues like SQL injections. So this then showcases that fuzzing is a very good tool in the toolkit for automatically securing software by generating inputs and monitoring for defects. But how does it fit into a microservice architecture? Where not only have the problem that it's hard to find bugs within one service, but actually the bugs can be caused from an interaction of multiple services spanning network call after network call. So how do you even test? So our solution is that we actually fuzz the same way that we would fuzz a single library or a single application, but we also distribute the fuzzing engines the same way as the services are distributed. So each service or to each service, we attach an agent, a Java agent, that dynamically onload instruments the JVM that runs that service and listens to inputs from our fuzzer. Or better said, the fuzzer sends these inputs to the first service. And since the agent instrumented the Java bytecode that makes up the service, the agent can send precise feedback back to the fuzzer about which parts of the code were ran when the service executed upon that request. And this is not only true for the first service in the chain, but actually for all services in the chain. So if you have like a top tier, mid tier, and low tier architecture, where one service dispatches to the second service and that dispatches to the third service and it all goes back, the agents can track the inputs across these network calls because they attach to all services. And this is really the great advantage of this highly distributed fuzzing, that you can now test deployments, whole microservice deployments, without much adaptation, in a highly scalable way. So how exactly does it work? And I will show you a bit more of how it looks like in CI Fuzz. But the summary of the 5 steps needed to fuzz complex distributed web applications is you identify which services you want to instrument. And then there's a fuzzing agent that comes with CI Fuzz that you need to add. So in most cases, if you're deploying on things like OpenShift or Kubernetes, you would add a sidecar that contains this fuzzing agent, or you would put the fuzzing agent directly into the Docker image and load it through normal Java, through a Java command line. Then you configure a new fuzz test. Jacob said in the beginning that this would be a coding session. Unfortunately, it's really no code. So you just click on the endpoints that are automatically detected by the fuzzer. Optionally, you can add existing HTTP requests as seeds. This is required when you have a logged-in, for example. So these, I can show you how these requests look like. They are basically dumps of what you get when you log in with your username and password to the platform or to the software under test, and record it with your browser development tools. And then you run fuzzing until your service crashes. And the 5th part is actually the one that generates the value and the one that you want to run continuously as part of your continuous integration and continuous deployment pipelines. So every time you deploy, or every time you deploy to a staging environment, you will also deploy to a fuzzing environment, where the fuzzing agents attach to the JVM, and where then the fuzzer supplies random inputs to your application. In the same way that you do API testing and smoke testing on the staging deployment, you do random fuzz tests in the fuzzing deployment. So with that said, I would like to switch over my screen to the web browser. Or in the meantime, are there any questions so far? So otherwise, I'll just switch to my browser window. So, Jeremy had two questions. Does that mean it will auto-detect the places to create fuzz tests? Yes, in the web case, definitely. So if you have a custom C library, then it's hard to auto-detect what the function, what the software does. But since web applications are very standardized, so for example, you use Spring Boot, or you have an open API, open API or Swagger definition, we can use that information, or we are using that information to automatically generate the fuzz tests. Okay, so here I am in a software called WebGoat, which is a web service that is deliberately insecure as basically a showcase of all the different types of security issues you can have when developing web software. And what I would like to show you first is how CI Fuzz integrates into development, especially on GitHub or any other code hosting platform. So here, for example, you have a merge request that sets up fuzzing to test all endpoints. And similarly, you would have a request that generates, that contributes a new feature, for example, but also introduces a new bug. So here you can see that fuzzing ran as a GitHub action, so it's directly integrated into GitHub. You can see the code coverage actually that what all was covered by the fuzz test. You can see that lots of lines were touched by fuzzing, and especially you see that an SQL injection was found while fuzzing. So you can click here to view the finding. I just need to remember the tab that so that I don't get lost. And there you can see that this triggered an SQL injection by just trying out a funny character there. And this then broke the SQL prepare query statement. Therefore, this is a possible SQL injection. And so here you have then all the information you need as a developer to replay this finding. And you can see here a list of all findings that we found in fuzzing. One question from the chat was how we can look at the coverage. So here, here in the coverage, you only see which files were covered. But when you when you open up the program locally, you can also see the coverage overlay, so you can see which files actually were covered. But this platform actually does not store your source code, so your source code is private to your organization, but actually that source code is needed to produce these the precise coverage maps. So this is a step then that you can only do locally. But in the back end, we are using Jacoco, which is the de facto standard tool for coverage in the Java world. And so you can get the Jacoco files that correspond to the fuzzing runs and then post-process it locally. So actually, everything that I'm showing you here, you can also try out at home at app.codeintelligence.com, where you can log in with GitHub, and then you can view all our demo projects. For example, we've also set up WebGoat here. And here you can also then see all the findings. You have also a bit of a summary of how fuzzing was set up. And especially what I would like to highlight is to handle the common case of authentication. So here you can see that we have a simple HTTP file that we dumped into the Fuzz targets folder that then is transmitting a username and a password to the server. And the fuzzer then, from time to time, picks up this initial request and uses that request as part of the fuzzing chain, so to say. So it interacts with the program, with the service, in the sense that it sends the first request, gets the cookie, sends a random request, gets the cookie, sends a random request, and repeats that chain for a while until it reached enough coverage, and then starts up a new chain of requests. So it really interacts with your application like a human or like an attacker would. So this is something you can check out right now. So this repository is public. This web app is public, and you can also dig through the list of all the findings. We not only find SQL injections, but also check for common security headers. So for example, the absence of CSRF tokens. So another question from the chat is, when I'm using SAML or Okta, so for complex multi-party authentication systems, we found it the easiest to test to just encode something like a long-lived bearer token in the fuzzing deployment that the fuzzer can then use. And then for the authentication, you would then probably leave the request body empty here, but just put in a header that then contains the token you need for authenticating. Doing it any other way, you can also put here requests to other services, but this then adds a lot of interdependencies, especially if you then need to be logged into another single sign-on system. So how we recommend to use fuzzing within your development process is really to have a separate environment, stage, namespace, where you deploy your fuzzing server to. And in that fuzzing environment, in that fuzzing setting, you can then generate a long-lived token. I hope that answers your questions about SAML. I mean, it always depends on what you kind of want to test, but yes, I would recommend a long-lived token. Yeah. So I think I answered. Yeah, thanks for that question. Here really, I mean, so the power of fuzzing that I should mention here is that for every bug that we find, it's not a speculation in terms of maybe this could have led to that other thing, but it's really we have seen the behavior that caused this bug directly being tied to one input. So in this case, for example, this SQL injection that then created this big stack trace was caused by this curl command. And this seems like a nice to have, but it's a really core functionality where the paradigm that you would have for static analysis really shifts in the way developers interact with fuzzing versus static analysis. Because here, the developer can just copy that curl command, start up his local service, and execute that curl command and see the exact same behavior. So in this case, you have no false positives, but every finding is tied to an input, and every input is then tied to behavior of the system in the wild. This is also true if you test the whole microservice deployment. because then you don't have like, okay, this individual service might be vulnerable to when getting this input, but that could never happen. If you fast test the whole deployment, start from the API server downwards, then you basically are sure that every finding is real, because it is really real, if that makes sense. So this was all that I wanted to show to you today, unless there are more questions or more things that you would like to see. So in any case, you can find the app on just this link, where you can explore our demo projects and get a deeper understanding of how fuzzing can help you to find different bugs. So here we don't only have Java projects, so WebGoat and the JSON sanitizer are Java projects, but also C and C++ projects, if that's interesting to you. So in this case, you can get a good overview of the capabilities of fuzz tests. Okay, then I would say thank you for your time, and thanks especially for everyone that asked questions. Jacob, do you have questions? Or?
So thank you, Henning. Yes, I would like to know more. Like, how can I use this demo? Like, how do I can get access? How should I use it? What should I do if I have troubles with the directory?
Okay. Yeah, sure. So so you can just go to the link that I posted, which is on app.contingents.com. When you log out, you can sign in with any GitHub account, and that basically then directly takes you to the page where you can explore these demo projects. So we're constantly updating functionality on that platform to onboard more example projects, as well as also to make it more interactive in the future. So stay tuned. But you can already explore this in your own pace to get an idea of what fuzzing looks like if you were to do it. Because ideally, fuzzing is something that you set up once for your API endpoints, and then it runs continuously when you develop. So those views are really the ones that your developers interact with when they look at what are the findings caused by the latest run. I mean, WebGoat is intentionally insecure, so you have hundreds of bugs, but usually software is a little bit more stable for what we see at customers. Yeah, so but you can really just start exploring